Hello everyone, today I'm going to talk about the paper Identity Preserved Transform, understand what activity classification models have learned. The presentation consists of 4 parts: motivation, method, experiments, and summary. Let's start from the motivation first. Thanks to the prosperity of convolutional neural networks and deep learning algorithms in recent years, activity classification models have developing rapidly. The performance on small datasets like HMDB51 and UCF101 are almost saturated, yet their performance on larger datasets like kinetics and moments in time are relatively low. Besides, research has found that it is difficult for these CNA-based models to generalize to new datasets other than training datasets and real-life scenes. Therefore, in this work, we mainly want to study what leads to the performance gain on the model and what the models have learned after training. Corresponding to this problem, we propose a method called Identity Preserved Transform. IPT is inspired by video data generation process. Its core idea is to manipulate nuisance factors and keeps essential factors unchanged. Essential factors are the factors directly related to the task, denoted as P, and nuisance factors are those not directly related to the task, denoted as theta. If we denote the data generation process as function g, then the generated data can be expressed as I equals g p theta. Assume that we can find the transform t theta that equals the effect of manipulating nuisance factors theta during data generation. We expect a good model can keep its performance as long as p remains the same, as expressed by this equation. Deriving from this insight, we separate identity preserved transform into 2 types. One is image space transform, which operate on generated data I. The other is 3D transforms, which operate on theta during data generation process. For the task of activity classification, we consider human motion as the essential factor and other factors such as background, viewpoint, human appearance as the nuisance factors. What's worth noting is that our experiments are designed mainly for activities weakly related to the context, but our method is suitable for all kinds of activities, as long as we include all factors related to the definition of the activity into essential factors. Further on, we propose 3 types of IPT for the task of activity classification: image processing transform, semantic transform, 3D transform. To show the effectiveness of our model, we conducted experiments on 2 models: temporal segment network trained on UCF101 and inflated 3D network trained on kinetics. Next, I will introduce the specific 3 types of IPT with our experiments. The first is image processing transform. It includes image processing techniques widely used for data augmentation, such as adding noise, blurring, grayscale, etc. We apply this type of IPT to the whole UCF101 dataset and retest TSN's classification performance. Results show that though these image processing techniques preserve human motion information in the video, they lead to serious dropping of accuracy. For example, adding additive Gaussian noise caused a drop by 24% of accuracy for the riding bike activity. The second is semantic transform. We use mask RCNN to generate foreground-only videos and background-only videos for UCF101 as shown in these 2 figures. Then test the TSN to get classification accuracy changing rates for each activity class. After applying semantic transform on all UCF101 classes, the activities in this black box caught our attention. TSN failed to recognize these activities using the silhouette in the foreground, but achieved high accuracy using only the background. This means the model has overfit to the background over these activities. In addition, the results given by semantic transform is supported by class activation mapping. In diagnosing a model, Class activation mapping provides qualitative diagnosis, and semantic transform provides quantitative diagnosis. Image processing transform and semantic transform both belong to image space transform. The third IPT approach is 3D transform. Considering it is difficult and expensive to achieve 3D transform on real video data, we implemented 3D transform on computer-generated animation video, then verified the conclusions by real data. Our synthetic activity data are collected from the Epic Games Marketplace and the CMU mocap dataset. Next, we use two instances to demonstrate the implementation of 3D transform. First is studying the influence of viewpoint. We change the azimuth angle of the camera, and by recording TSN's classification score curve, as well as visualizing the PC embeddings from the intermediate features from the network, we found that TSN model is most sensitive to the viewpoint from the flank when recognizing push-ups. Later, we verify the conclusions by experiments on real videos under a similar experiment setting, and the conclusions is also supported by the real data. The second instance is studying the influence of the human appearance. We recorded top 1 classification accuracy of TSN I3D on different synthetic human appearances, while other factors remain the same, and found that both models show preference for some specific human appearances, as shown in the table. In summary, identity preserved transform is a method to diagnose what a model has learned after training from the view of data probe. In the paper, we also propose a data generation pipeline to achieve IPT, which includes image processing transform, semantic transform, and 3D transform. Our method intends to find out what aspects the model has learned to achieve good performance, and the reason why the model is prone to learn these aspects is left for future work.